This is the last video for the chapter. Yay! Let's go ahead and get started. We're going to be talking about the strength of acids according to their structure. And then at the end, we're going to wrap up the chapter by talking about Lewis acids and bases. All right, let's get started. So, the effect of structure on acidity. We can start here by thinking about basically the fact that the molecular structure determines whether a hydrogen atom in a molecule is ionizable at all, meaning that the molecule might have many hydrogens, but only some of them might actually be what we call labile hydrogens, meaning that there are hydrogens that can be donated. So for example, the acetic acid, even though it has a total of 4 hydrogens, only one of them, the one on that carboxylic acid, has the potential to be donated. That's only one labile hydrogen, okay? So the structure is what determines whether that hydrogen is ionizable or not. Also, the molecular structure determines how easy can that labile hydrogen be donated. Some of them can be donated easier than others, and the structure is going to tell us that. Now, if the hydrogen is easy to be donated, then that means that you have a stronger acid than if the hydrogen is harder to be donated. All right, so how do we predict the trend of acidity between different acids? There's going to be 2 different sets of rules. There's the rules for binary acids. Binary acids are the acids that have hydrogen together with one other element plus one element. And that other element is going to be a nonmetal. So examples of these binary acids would be something like HF or HCl or H2S or H2SC or something like that, right? Hydrogen plus one other nonmetal element. Now, the trend in terms of the increasing strength of acidity is that within a period, which is a horizontal row of your periodic table, the acidity increases from the left to the right. And the reason for that is as we go to the right, that other element, meaning the fluorine or the oxygen, has a higher electronegativity, which means that it will be pulling the electrons to itself, leaving the hydrogen kind of loose. And so the hydrogen would be easier to be let go than if it is more tightly bound, right? So as we go to the right, the acidity increases, meaning that it's easier for HF to donate a proton than it would be for CH4 to donate a proton. Now, within a group, which is a vertical column in the periodic table, the acidity will increase with increasing atomic number, meaning that the acidity increases as we go down. And the reason for that is that as we go down, the size of the atom increases. And when the atom increases, the overlap in the orbitals that are taking part of the bonding process between the hydrogen and that other atom, the overlap decreases. And so the hydrogen in HF is much more tightly bound than the hydrogen in HBr, because Br is a much larger atom and therefore the overlap is less. All right, so from here, what you really need to remember is that the trend for a binary acid increases as you go to the right and as you go down, right? So that is a trend that I want you to remember. An acid that is to the right and to the bottom is going to be stronger than one that is to the left and up. The second set of rules is for oxyacids. Oxyacids are acids that contain hydrogen. They contain another non-metal element, and they contain oxygen, which is what's different from the binary acids. The binary acids did not have oxygen. Okay, so the rules for oxyacids will depend on whether the acids have the same structure or whether they have the same central atom. When I say oxyacids that have the same structure, What I'm talking about is acids that have the same number of hydrogens and the same number of oxygens. So the only thing that they differ on is that central atom, like for example here, chlorine versus bromine. So coming back to the rule, for oxyacids that have the same structure, the acid strength increases with electronegativity of that central atom. Remember that the electronegativity increases as we go to the right and to the top of the periodic table. So for example, fluorine, which is to the top and right of the periodic table, would have the highest electronegativity. Something like oxygen or something like chlorine would have a lower electronegativity than fluorine. All right, so coming back to this example, here we're comparing HClO versus HBrO. We think about the position of chlorine and bromine on the periodic table. The chlorine is higher up than the bromine, meaning that it has a higher electronegativity, and because of that, HClO is going to be a stronger acid than HBrO. Similarly, we go to the second example where we have HClO3 versus HNO3. They have the same structure, meaning the same number of hydrogens and the same number of oxygens. And of course, if we compare the position of chlorine versus nitrogen, chlorine is closer to fluorine than nitrogen is. Therefore, this acid is going to be stronger than the nitric acid. All right, now the second set of rules here for oxyacids is oxyacids that have the same central atom, meaning in this case chlorine. We have chlorine, 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 and chlorine. The acid strength is going to increase with increasing number of oxygens attached to that central atom. So hypochlorous acid, which is HClO, compared to chlorous acid, which is HClO2, versus chloric acid, which is HClO3, versus perchloric acid, which is HClO4. So notice that all of these acids contain that same central atom, but they differ in the number of oxygens. Basically, the higher the number of oxygens that you have, the stronger the acid. So the perchloric acid, which has four oxygens, is stronger than the chloric acid, and those two are stronger than the chlorous acid and than the hypochlorous acid. And hopefully you're able to remember this because you guys know that these two, chloric acid and perchloric acid, are categorized on our list of strong acids. But chlorous acid and hypochlorous acids are weak acids. So we can see that as the number of oxygens increases, we actually go to the strong acid category. All right. Clicker question for you guys. Which of the following oxyacids is the weakest? And I want you guys to try it at home. Go ahead and pause the video. If you need a little bit of help, what I want you to do is to compare pairs, like two pairs step by step, starting by looking at acids that have the same structure or acids that have the same central atom, and from there start kind of ruling things out one by one. All right, pause the video, give it a try. And now let me tell you how I did it. So I started by comparing A and D. Between those two acids, they're both oxyacids. They have the same central atom. And so what I'm going to be looking is the number of oxygens, right? So between this and this, the one at the bottom has 4 oxygens, which means that this is a stronger acid. In this particular problem, I'm looking to see which one is the weakest. So out of those two, I can actually rule out H2SeO4 because that one is stronger out of those two. I did then the same thing for these two acids. Between those two acids, they both have sulfur as the central atom, and so the difference is the number of oxygens. Out of those two, sulfuric acid is the stronger because it has more oxygens, so I can go ahead and rule that one out. Now I'm left with A and B, and if you notice, both of those have the same structure, meaning that they have the same number of hydrogens and they have the same number of oxygens. And so what I need to do is to compare the electronegativity of that central atom. I have selenium versus sulfur, right? If you go and look at the periodic table, you will see that sulfur is closer to the top and to the right of the periodic table than selenium. So the sulfur one is going to be stronger acid. So our answer to this particular problem was that H2SeO3 was the weakest out of all of the acids in this list. All right. From there, we go to what are the reasons for these acidity trends? Well, there's a number of things that play together in order to give us those trends. The first of those is bond polarity. Remember that bond polarity means what is the difference in the electronegativity between the two atoms that are bonded together. The higher that polarity or the higher the difference in the electronegativity, the stronger the acid. And the reason for that is that if you have an atom like an oxygen or a fluorine, which is very electronegative, then it will try to pull electrons toward itself, thereby allowing that hydrogen to be more easily released. Now, the other thing that affects the acidity trend is the bond strength. The stronger the bond, the more energy would be required to remove the hydrogen, and therefore the weaker the acid. And the bond strength is higher if you have smaller atoms than if you have bigger atoms. The next thing is the anion size. The larger that anion, meaning chloride or bromide or fluoride, the larger it is, the smaller the extent of overlap between the orbitals, and therefore the weaker the bond between the hydrogen and that anion. And finally, the stability of the conjugate base is also important. The greater the stability of the conjugate base, the stronger the acid. And in this class, we haven't really talked about the stability of the conjugate bases. This is something that you will learn a lot more about in organic chemistry. So all of these four factors play together again to give us the overall trend in acidity. What I would recommend is that you guys learn the trends from the previous 3 slides and utilize those and apply those rules for any kind of binary acid or oxy acid that I can ask you. Okay? All right. Finally, we move on to Lewis acids and bases. And to do this, I'm going to go back to a slide that we had at the very beginning of the chapter. That was slide number 10. In that slide, we had talked about the 3 different definitions of acids and bases. We talked about the Arrhenius acids and bases that were basically substances that increase the concentration of either hydrogen ions or hydroxide ions in solution. We then talked about the Bronsted-Lowry acids and bases, which were proton donors and proton acceptors, respectively. And now we're moving back to the Lewis acids and bases. Notice that a Lewis acid or base has to do with the electrons as opposed to protons. Remember that protons were the hydrogen ions. Here we're talking about electrons. And notice that a Lewis acid is going to be an electron pair acceptor, which is the opposite from the Bronsted-Lowry definition. But now we're dealing with electrons. And then a Lewis base is an electron pair donor. Look at the donor versus the acceptor for the Bronsted-Lowry, but of course the Bronsted-Lowry was talking about protons. So we're talking about different things that we're accepting or donating. In this case, electron pairs that are being accepted by the acid and that are being donated by the base. All right, so knowing this, let's go to the next slide, which talks about how do we identify a Lewis acid or a Lewis base. So a Lewis acid, we said, is an electron pair acceptor, right? That's going to include compounds that have a central atom that has less than an octet on it. And those are typically going to be compounds that have either boron or beryllium as the central atom. Notice that the examples that I have listed, they all have boron or beryllium bound to a very electronegative atom such as fluorine or chlorine. Another set of compounds that act as Lewis acids are going to be compounds that have double or triple bonds on that central atom. Because basically they would be able to accept an electron pair and be able to bind to something else. And finally, cations. Cations are positively charged ions. Those would be happy to accept electrons, so thereby they make good Lewis acids, good electron pair acceptors. Now, our Lewis bases, these are electron pair donors. They are going to constitute compounds that have non-bonding electron pairs that are able to be donated. For example, here in ammonia, notice that lone pair of electrons that is available to be donated. And another set of compounds that could act as Lewis bases are going to be anions. Anions are negatively charged ions, and those anions would be happy to donate the extra electrons so as to not be charged anymore by actually binding to something. So in the example that we have down here, notice that we have this boron compound that only has 6 electrons on that central atom. So that makes it one of these cases, a compound where the central atom has less than an octet. So this guy is going to act as our Lewis acid. And then here we have ammonia, which has that lone pair of electrons. This is going to act as our Lewis base. And the Lewis acid is going to be accepting the electrons, the Lewis base is going to be donating the electrons, and they're going to come together and form this covalent bond between the two. That covalent bond is formed by the sharing of that pair of electrons between the two. All right. So in this last slide, I just wanted to show you guys some examples of Lewis acid-base reactions. In this particular slide, everything has been organized in such a way that the first compound is actually a Lewis acid, and the second compound is our Lewis base. Remember that the Lewis acid is going to be the electron acceptor, and so we're talking about either cations or compounds that have a central atom that has less than an octet, right? And then the Lewis bases are going to be the electron donors. And so these are going to be compounds that have a lone pair of electrons available, such as ammonia, or they might be anions, right? So as you can see, the Lewis acid is going to be accepting electrons. The Lewis base is going to be donating electrons, and they're going to come together and either form a complex. These are known as complex compounds, or they're going to undergo what is known as a hydrolysis reaction to be able to form this other complex. Now, we will not be asking you to predict the products of this kind of reaction, but I will be asking you to be able to identify out of those reactants which one is acting as the Lewis acid, which one is acting like the Lewis base, which one is donating electrons, which one is accepting electrons. All right, guys, that is the end of the chapter. Yay! Have a great day. Bye.